Welcome to the Explainer. We're going to tackle a question that sounds super simple, but the answer, well, it's anything but. How much does a cloud actually weigh? Okay, let's dive right in. We've all done it, right? You look up at those puffy white clouds just drifting by, and you think they're basically weightless. But what if I told you that just one of those clouds weighs more than a whole herd of elephants? Yeah, let's find out how on earth that's even possible. So, it's all about perception versus reality. We see them as these, ethereal, weightless bits of cotton candy in the sky. But that's just not the case. The truth is, they are absolutely immense objects, forces of nature, carrying a weight that is, frankly, just staggering. All right, so how in the world do you even begin to weigh something that you can't, just pop on a scale? It sounds like a riddle, doesn't it? But it turns out one scientist figured out a surprisingly clever way to do it, and all she really needed was some pretty basic math and her car. And that scientist is Peggy Lamone, a researcher at the National Center for Atmospheric Research. She's the one who really cracked this puzzle. And what she came up with was this beautifully simple, really elegant three-step method to figure out the weight of a cloud. So here's her methodology, and what's so cool about it is how it breaks this impossible-sounding task into 3 totally manageable parts. Step 1, you measure the cloud's density, basically how much water is packed in there. Step 2, you calculate its volume, so how big is it? And then step 3, you just multiply those 2 numbers together to get the mass. Simple, right? Well, let's break down each one. Okay, first up is density. Scientists call this liquid water content, or LWC. For a typical everyday cumulus cloud, one of those puffy white ones, it's only about half a gram of water per cubic meter. Now, to put that in perspective, that's like taking the amount of water in a single small marble and spreading it throughout a room big enough for 2 people. It sounds like almost nothing, right? Incredibly small. But just hang on to that thought, because here's where it gets crazy. That tiny density gets multiplied by a truly massive volume. And Lamone's method for figuring this out was just ingenious. She literally just measured a cloud shadow. She waited until the sun was directly overhead, drove under the shadow, and watched her car's odometer. What she found was that a typical fair weather cloud is about 1 kilometer long, 1 kilometer wide, and 1 kilometer tall. Do the math on that. That's a volume of 1 billion cubic meters. So what happens when you multiply that seemingly tiny density by that absolutely enormous volume? You get a number that's just hard to wrap your head around. 500 metric tons. That's 1.1 million pounds of water. Just floating right over your head. And to really get a sense of that scale, what does 500 tons even look like? Well, that one little puffy cloud you see on a sunny day, it weighs the same as 100 full-grown African elephants, or 300 passenger cars, or more than 2 Boeing 747 jumbo jets, just up there. Okay, this, of course, leads to the big, obvious question. The floating paradox, right? If a cloud weighs as much as 100 elephants, why the heck doesn't it just fall out of the sky? Well, it's a combination of 3 key things. First, all that mass is spread out across trillions and trillions of microscopic water droplets. They're so small that air friction holds them up. Second, you've got updrafts, rising columns of warm air that act like an elevator, constantly pushing the cloud upwards. But it's the third reason, buoyancy, that's maybe the most counterintuitive and the most interesting. So here's the secret sauce, and it's gonna sound totally wrong at first. Moist air is actually less dense than dry air. I know, it feels backwards, but it's just basic chemistry. See, the air around us is mostly made of heavier molecules like nitrogen and oxygen. But when water vapor, good old H2O, enters an air parcel, those lighter water molecules literally push out the heavier nitrogen and oxygen ones. This makes the whole chunk of cloudy air lighter, more buoyant, and that causes it to rise. It's almost like a hot air balloon, but with water vapor instead of hot air. All right, but here's the thing. If you think 500 tons sounds heavy, oh man, we are just getting started. That was just for a tiny little fair weather puff. What happens when we start looking at the really big clouds? It turns out not all clouds are created equal. They have different densities. You know those thin, wispy cirrus clouds high up in the atmosphere? They're really sparse, not much water in them. But then you get to the big, dark, towering cumulonimbus clouds, the thunderstorm clouds. The amount of water they park into every single cubic meter can be up to 6 times higher than our little cumulus cloud. They are, by far, the most water-packed clouds out there. So you take a bigger cloud that's also way denser, and you get a lot more weight. A single mature thunderstorm system can be holding up to 2 million tons of water. We're not talking about 100 elephants anymore. This is the equivalent of 200,000 elephants floating in the sky. And then you have hurricanes. They're on a whole other level. At any given moment, an average hurricane is carrying something like 20 trillion pounds of water. To try and picture that, that's the same weight as more than 360,000 blue whales, just moving across the ocean. In fact, the rainfall from these monster storms is so unbelievably heavy that it becomes a genuine geophysical force. I mean, this is amazing. After Hurricane Harvey hit, scientists actually measured this. The sheer weight of the rain that fell, 127 gigatons of it, literally weighed down the Earth's crust so much that it bent downwards. Okay, these numbers are they're mind-boggling. But this is more than just a cool piece of trivia. Understanding how much clouds weigh has some seriously important real-world implications. So beyond the wow factor, why does any of this really matter? Well, take a look at this. It shows where all of Earth's water is. And you can see the atmosphere holds this teeny tiny, almost invisible sliver of it, just 1,000th of 1%. But that tiny fraction is incredibly dynamic and ridiculously powerful. It's what drives our entire weather and climate system. And that's why cloud weight is so critical. For one, it's a huge piece of the puzzle and one of the biggest uncertainties in our climate models. We've already seen how it has a real geophysical impact, right? It can literally bend the planet. And on a more everyday level, the next time your satellite TV glitches or your GPS gets a little wonky, it could very well be because of the sheer weight of water in the air that the signal has to pass through. So the takeaway here is pretty profound. The next time you look up at the sky, remember what you're actually seeing. It's not just some weightless puff of vapor. You're looking at a true force of nature, a heavy lifter in our global water cycle, the very engine of our planet's climate, weighing hundreds, even millions of tons, and powerful enough to literally move the world.